So, hello everyone. In today's discussion, we'll talk about the concept of t-square statistic, and we'll discuss the meaning of this statistic. So, I'll advise you to first go back and watch the discussion on the Q statistic. Only then you'll be able to understand this t-square statistic, because the t-square statistic calculation involves actually first calculating the Q statistic. So, first is the difference between tau square and t square. What is the difference between tau square and t square? See, tau square is basically the parameter and t square is the estimate. That is the main difference. So tau square is the variation in the true effect size. So imagine if you had infinite number of studies and each study had an infinite sample size, then the variation in the true effect size that you would observe, that would be the tau square. But unfortunately, you cannot have infinite number of studies and you cannot have each study with an infinite sample size. So you can only estimate the between study variance, right? And that estimated between study variance, that is the t square. So you can simply say tau square is the population parameter, whereas t square is an estimate of this parameter, right? And just to revise, we have already discussed this concept in discussions of random effect modeling. So there are two types of variance, you know that. One is the between study variance, and this study variance depends on the sample size of the individual study. If a study has infinitely large sample size, then this within study variance would amount to 0, because there would be simply no sampling error. Another variance, which is the actual or the true variance in the effect size between studies, that is the t square or tau square. Tau square as in this is a parameter and t square is what we estimate. So this is the between study variance, and this is the true variance in the effect size, the actual variation in effect size which is occurring from study to study. So this is what we are going to talk about in this discussion. We'll talk about the between study variance. So that is the t square. So now what is the formula of t square? You know that in random effect modeling I discussed this formula, q minus degrees of freedom by c, or the quantity. So this numerator will make sense now after that because we have already discussed the q statistic. You know that what is q? Q is the observed weighted sum of squares, right? So it is basically, you can say, it is the observed amount of dispersion in a way. And what is degrees of freedom? Degree of freedom is the expected amount of dispersion if all the effect sizes, they were same, common across all the studies, and whatever variation was there, it was purely due to random error. So this is the expected amount of dispersion and this is the observed amount of dispersion. This concept has been discussed in the video of Q statistics. So I would advise you to go back and visit that video before you watch the video on t square statistic. So because I have discussed this concept that whatever excess dispersion is there, right, the excess dispersion in Q more than df, that would be taken as the true dispersion, or the like the heterogeneity basically. So we assume initially that we ask ourselves what would be the expected dispersion if there was only random error happening and there was no true variation in effect size. So that would be the degree of freedom, right? And then we ask ourselves, okay, what is the actual observed amount of dispersion? So if the observed amount of dispersion is more than the expected amount of dispersion, it simply means that this excess dispersion is because probably there is some real variation in the effect size, right? And if the observed dispersion is less than this expected dispersion, means q minus df is less than 0, then we'll say that there is no heterogeneity. So if q minus df is more than 0, it means that yes, there is heterogeneity. And if q minus df is less than 0, it means observed dispersion is less than what was expected just by random sampling. So it means that there is no true dispersion, right? So now what happens is, the problem with Q statistic, we have discussed this, that it is not on the original scale. First of all, it is a standardized measure. So it is, you can say it is analogous in some way to standardized mean difference, which is the effect size estimate, right? So like Q statistic is standardized, so it is not on the original metric. That is the first problem with Q statistic. Another problem with Q statistic is that it is sensitive to number of studies. it's not a problem, it's also a use, because of these properties we use q statistic to compute the p values for to test the null hypothesis of test of heterogeneity. But this is also a problem in the sense that q statistic is not intuitive because of these reasons. Because first reason, it is not on the original metric scale. Second reason is that it is a sum. Okay, it is a weighted sum of squares, right? So it is a sum, and it is not very intuitive to think about like a statistic which is a sum. So because of these two reasons, we want a statistic which gives us more intuitive idea about how much amount of dispersion is there in the original metric. Okay, so that is why we need the t-square statistic. So there are two great properties of this t-square statistic. This is all that is practically important for you to understand. The t-square statistic first property is that it is on the original scale. So whatever effect size index you are having, right, x correlation coefficient, or standardized mean difference, or odds ratio, whatever metric you are using, it is on the same scale. Like t square is obviously the square of that scale, but t is on the same scale, right? So that is a great property. It makes it intuitive to understand and to think about the t statistic. Second property is that it is an average, not a sum, and it is more intuitive to think about averages rather than sum, right? So how do we compute it? Q minus df, which is nothing but the excess dispersion, divided by c. And what is c? This we have seen in discussion of random effect modeling. It is sum of the weights minus sum of the weights square divided by sum of weights. And here w basically means the reciprocal of within study variance. Remember that the weights as they are computed in a fixed effect modeling, that we will be representing simply as w, and it will be the inverse of variance. Whereas when weights are used as per random effect modeling, then I'll be denoting it with a star. Okay, so w star, and that would be the sum of the variance within study variance and between study variance. Okay, so now basically you understand that it has two properties. First is it is on the same scale, same metric but squared, like t square will be on the same metric but squared, and t will be on the same metric. And second great property, it is that it is average, not a sum. So that these two properties make it very intuitive to understand. It's very intuitive statistic. Now so what happens when q minus df is less than 0? So let's say df is 5. You have 6 studies, so your degrees of freedom will be 5, and the q statistic that you calculate, you remember how to calculate the q statistic. I'll just show you the formula. This is the formula you'd be using. So it is the sum of product of weight and the effect size square. Remember the weights here are the inverse of the within study variance, minus sum of the product of weight and effect size square divided by sum of the weights, right? So this is your observed dispersion basically, or observed weighted sum of square. So you have computed q, then you computed df, then you have to divide this with c, or the quantity, and quantity you will use this formula, right? So now the point is, imagine if this q minus df is less than 0. I was telling you, imagine q is 3 and degrees of freedom is 5. So q minus df is obviously less than 0, right? So the thing is that t square can never be in negative, right? Even though q minus df will be negative in this case, like 3 minus 5 will be minus 2, right? So but you would, if it is in negative, you just take it as 0. Okay, so the actual variance, obviously the actual variance can never be in negative, right? So if it is coming as negative, if q minus df is coming as negative, if q minus df is less than 0, then t square is basically simply taken as 0, right? Second thing, again, if q minus df is more than 0, then of course you know it will be positive only, so you don't have to think a lot. So just remember this, if q minus df is less than 0, and if the t square statistic comes as negative, you will simply set it to 0. Now the question is, what does this t square depend on? So it depends on two things. First thing, you can already see it depends on the amount of dispersion. If there is too much dispersion, if the value of this is q minus df is nothing but excess dispersion, so if the amount of dispersion is more, then t-square statistic will be more. But second important thing is also the scale, and I'll show you with some examples how it depends on them. Okay, so just remember for now that it depends on two things. First, it depends on the excess dispersion, which is the numerator in the formula, which is q minus df, but it also depends on the absolute dispersion or the scale. Okay, so even though it is possible that excess dispersion will be same for two studies, but t-square will come more because the scale of one study will be like bigger than the scale of other study, and I'll show you this shortly. So what all we have discussed till now, we know that the tau square is the variation in the true effect size, and it is a population parameter. It is a hypothetical concept if each study had infinitely large sample size and there were infinite number of studies. Whereas our sample estimate of this population parameter, this is the t-square. So this is the observed variance in the true effect size. And this is because each study has a limited sample size and there are only limited number of studies. So that is the difference between tau square and t square. This is the formula for t square. When we divide the excess dispersion with c, what this does is it converts the q statistic into the original metric back again, and it also converts it into an average rather than sum. So these two properties are really important for t square statistic, that it is on the original metric and it is a average rather than a sum, which makes it a more intuitive statistic as compared to the q statistic. So the only purpose of a q statistic is to test the null hypothesis, to compute the p-value. But remember, q statistic can never be used to see how much amount of dispersion is there. And again, we have discussed this in previous lecture, that even if a p-value of test of heterogeneity is significant, it can mean two things. It can mean either there is truly large heterogeneity, or there is maybe small heterogeneity, but you had a lot of studies, right? That's possible. You had a large sample size, or you had a large number of studies. And the opposite is also possible, that if a p-value of a test of heterogeneity is coming as non-significant, it is coming as significant, it can mean that there is a large heterogeneity, or it can mean that there is no heterogeneity. So see this, if the p-value is significant, it can mean there is large heterogeneity, but it can also mean that there is small heterogeneity with large number of studies. Similarly, if it is a non-significant p-value, it can mean either there is truly small heterogeneity, or it can mean that the heterogeneity was large but the sample size or the within study sample size was too less, like the sample size or the number of studies were too less, because of which p-value could not come significant. So the point is, p-value is not a reliable estimator of how much heterogeneity is there. Okay, it cannot tell us for sure how much heterogeneity is there. It cannot account for the amount of heterogeneity. It can only help us to know whether there is enough evidence to claim that there is heterogeneity or not. So it can only be used to test the null hypothesis. It cannot tell us the amount of heterogeneity. For amount of heterogeneity, we use the t-square statistic. So now I'll show you two examples of how the t-square statistic is depending on excess dispersion as well as the scale of dispersion. So let's look at these two forest plots. What you can see, we'll discuss from the beginning. We'll start from the q statistic only. So you know, for q statistic, it is the ratio of the observed variance with within study variance. Okay, first I want you to pause the video and look for yourself, for which forest plot do you think the observed variation is more? Remember, observed variation is the difference between the summary effect and the effect size of individual studies, right? So study effect minus summary effect square. So obviously you can see the position of these squares are same. Okay, if you will notice, the positions are same. The only thing that is changing is actually the variance. So the within study variance is less in here and more in here, but the center, the point estimate, you will say, is same, right? So the summary effect will also be same. So let's say this is the summary effect for both the forest plots. So now you can see that the observed dispersion is actually same, right? Because the difference between the summary effect and the individual study effects, it will be same only. The difference ka square, it will be same. So it is same for A and B. Now let's talk about within study variance. It is very clear that within study variance is much more for A than B. So within study variance is much more than for A than B. Now you know that Q statistic is nothing but the ratio of the observed variation within study variation. Because observed variation is same in A and B, but within study variation is more in A, so Q statistic will be less for A. Right, so Q statistic is the observed dispersion or observed weighted sum of square, and it will be less for A and more for B. Right, now we'll talk about Q minus degrees of freedom. Again, the number of studies is same for both of them, so degrees of freedom will be same for both of these forest plots, only Q is changing. So because Q is more for B than for A, again the excess dispersion or the difference between Q minus DF will be more for B than for A. Now because you can see that excess dispersion is more for B than A, you can say that when we do the test for heterogeneity and compute p-values, p-value will be more significant. Okay, and there is no such thing as more significant or less significance. Either you cross the threshold or you don't cross the threshold, but I've just written this to show more significant means it will be closer to 0. Okay, so just don't think of it like more or less significant, think of it like p value will be closer to 0 for which one of them. So we know because there is more dispersion, the Q minus DF excess dispersion is more for B than for A. So and the p value or the test for heterogeneity, it is based on this statistic only. So because of this reason, p value will be closer to 0 for B, right? So you can see for B it is closer to 0 than for A, right? Why? Because you can see the dispersion is more. Can you see, right? Q minus DF is more for which forest plot? For B forest plot. So p value will also be closer to 0 for B forest plot. Now we'll talk about the thing which is most important that we are discussing, which is the variance in true effect size or T square. So it will be more for B or A. So you can see that the Q minus DF, this is the numerator part is bigger for B, right? Because the numerator part is bigger for B, so we'll expect that the T square statistic will also be bigger for B, right? And because T square statistic is bigger for B, obviously T also will be bigger for B, right? Then we have not discussed this yet, but we'll discuss soon I square statistic. So I square statistic tells you how much proportion of the dispersion is contributed by the true variation in effect size. So that is actually bigger for B. Okay, so if you don't understand I square, just forget about this for now. So the point is that I wanted to say is like T square here depends on what? The conclusion is that it depends on the difference between Q minus DF, and that is obvious. If you look at the formula, it is Q minus DF by C. This is the formula for T square statistic, Q minus DF by C. So obviously it will depend on excess dispersion, and you can see the excess dispersion is more for B than A. Because of this reason, T square is more for B than for A. So this is what I wanted to show you, that when excess dispersion is more, right, excess dispersion is more, then the T square statistic will be more. So it depends on this excess dispersion or excess variation, right? This is the first thing it depends on. Now second thing it depends on is the absolute scale. So in this example you will see the excess dispersion is same. See, this Q minus DF or the numerator is same. Q minus DF is the excess dispersion. It is same for C and D. So do you expect the T square to be same for C and D? The answer is no. T square is still more for D than for C. Why is this? The reason is the scale of the D itself is more. Can you see the total amount of variance itself? It is more, right? You can see that for D there is more variance overall. So because there is more variance overall, T square will be more for D. Okay, so let's start from Q. We'll start comparing from the Q statistic only. So the first thing is the observed variation. You know what is observed variation? Observed variation is the difference between the study effects and the summary effect. So now the summary effect, it's not shown here, but let's imagine the summary effect is somewhere here for D, and it will be somewhere here close to the null line for C. So when you will compute the differences between these study effects and the summary effect, the differences will be more for D actually. Okay, so the observed variance, right, you can see, right, if you don't have to think too much also, you can see, like if I draw a line here, let's draw like this, right? How much deviation is there? Just look grossly, and then I'll draw a line like this. For which which line do you think is showing more like dispersion, observed variation? It is D for sure, right? So observed variation is more for D. Then we'll think about within study variance. So you can see easily within study variance is much more for D. So for D, observed variation is also more and within study variation is also more. However, because Q statistic is a ratio, it is a ratio. So when we take the ratio of the observed variation with within study variance, what will happen is the Q statistic will be same for D and C. So this is a great property of Q statistic. We have discussed this already, that it is a ratio of the observed variation to within study variation. So if the observed variation is more, you can see in D the observed variation is more, but the within study variance is also equally more. So because they are both increase, the ratio will remain same. So the Q statistic will be same for D and D and C. Similarly, the Q minus DF or the excess dispersion, it will also be same. Why? Because for both these forest plots, the degree of freedom is 5, right? Here also and here also it's 5. So Q minus DF will also be same for C and D. And because Q minus DF is same, again P value will also be same, because you know that P value is computed from this statistic only. So because the Q minus DF is same, you can see Q is 12. Why it is same? Because it is the ratio of observed variance to within study variance, which has increased equally in case of D. Both numerator and denominator has increased equally. Then Q minus DF will also be same. Then P value will also be same. Till now it is clear. Now let's talk about T square statistic. So you know that the T square statistic is basically Q minus DF by C. So you would expect, because Q minus DF is same between C and D, you may expect that T square will also be same. But I've told you it not only depends on excess dispersion, it also depends on the absolute scale, the scale of the dispersion also. So if I were to ask you, total variance is more for which forest plot? Total variance means within study variance as well as between study variance. Okay, so total variance is definitely more for D. You can see that in D, the scale of the dispersion is itself more. So the scale is increasing in D. Now because the scale is increasing in D, T square will actually become, if you will calculate, it will come to be greater for D than for C. So even though excess dispersion remains same, that is the Q minus DF will remain same, the C will be, the denominator will change. Okay, the denominator will be less for D, and hence the T square statistic will come higher for D. So conceptually you can think of it like, basically T square depends on two things. It depends on excess dispersion, but also depends on the scale of that dispersion. If the absolute value of the dispersion, which is Q minus DF, it is more, then T square will be more. But even if the Q minus DF or the excess dispersion is remaining same, but the scale of dispersion has increased, like for D and C, remember this example, the Q minus DF or excess dispersion is same, but the scale of dispersion is more for D than for C, so T square will be higher for D than for C. And again, I square statistic, you can see it will be same. So we'll discuss this I square later on, but basically what it means here is that 58% of the total variance is accounted by the between study variance. Similarly here also, if total we say there is 100% variance, then out of that 100% variance, 58% variance is contributed by the between study variance or the true variance in the effect size. So that is the meaning of I square. So in both the forest plots, the proportion of the true variance is actually same, right? The proportion of true variance is 58%. If there was total 100 units of variance, 58 units were contributed by the variation between studies. That is the true variation. However, despite this, the T square will come higher for D than for C. Why? Because it also depends on the scale of dispersion. So just remember these points, that T square statistic also depends on the scale of dispersion, right? So now talking about how this T square relates with the study weights in random effect modeling. We have discussed this, that the weights in a random effect model are the it is the inverse of the total variance, right? Whereas in fixed effect modeling, the weights assigned to each study, they are the inverse of the just the within study variance, not the total variance. But in random effect modeling we have to account for total variance, and total variance will be the sum of within study variance as well as between study variance. You know this, right? So this method of estimating the the method that I've told you, this method that I've told you, right, that t square is basically q minus df by quantity or c, right? So this method is this Simonian and Lade method. This is the method also called as the method of moments. So this is the method that we have used in our examples of random effect modeling also that we have done previously, right? But the thing, remember, with this method is that it does not make any assumption about the distribution of random effects. Okay, so this method, it does not make any assumptions about the distribution of random effects. So how random effects are distributed, it does not make any assumption like that. And the benefit of this method, it is very easy to compute. Even with hands and a simple calculator, you can compute the you can assign the weights to individual study. You just have to calculate the t square and the within study variance, right? So it is easy. But then there is another method also to assign weights in random effect modeling, and that would be to assign to compute the t square statistic, and that is the restricted maximum likelihood method. So the thing is, this method is actually little bit computationally more difficult. So this is why this Simonian and Lade method has been described here. But remember, the differences are likely to be small. And if because computational difficulties are no longer there, if you use like some software to compute this t square, then you should prefer the restricted maximum likelihood method. However, the differences are likely to be small. So we have talked about the t square, which was the variance, between study variance. And what was the purpose of between study variance? It tells you how much amount of dispersion is there. So Q statistic will tell you whether there is enough evidence to say there is heterogeneity or not. So basically it is helpful in testing of null hypothesis. Whereas t square will tell you how much variance is there, how much true, what is the amount of heterogeneity, right? So that amount is like t square is a more intuitive statistic for seeing the amount of that variance. Now we'll talk about the t or the tau. So t is nothing but the standard deviation. So it is nothing but the under root of this t square. So this is the standard deviation in the true effect size. So t square is the variance in the true effect size, but t is the standard deviation in the true effect size. And of course you can understand tau is the actual standard deviation, that is a parameter, and we cannot estimate the parameter. We can only we cannot calculate, know the exact parameter. We can only find an estimate of that parameter. So that will be your t, right? And of course t will be on the same scale as the effect size index. So t square is the square of the effect size index, and t is the exact same scale as the effect size itself, right? So remember, t square will be the squared value, but t will be on the same scale, right? And again, it will not depend on the number of studies. Unlike Q statistic, it will be on the same scale, and it is a more intuitive measure than Q statistic. Okay. So what is the purpose of having this t? This t is very intuitive. It is very helpful because it can give you an idea about the distribution of effect size. Okay, so let's assume the true effects are normally distributed. Then we can calculate a 95% confidence interval of the true effect size. How we will do that, I'll tell you. First, just be clear with the terminologies. So this tau is the actual standard deviation in the true effect size or the parameter, and the t is the estimate of this parameter, the estimate of standard deviation in the true effect size, right? Whereas tau square and t square, they are the square of the original metric or scale, whereas the tau or t, they will be on the same scale as the effect size index, right? So now I want to tell you what is the practical importance of the t or the standard deviation in the standard deviation of true effect size, right? So let's see A and B. We'll see these two forest plots. So we'll start with Q. So you can see that the Q is more for B than for A. Means the observed dispersion or the observed weighted sum of square, it is more for B than for A. If you want to go further, you know that Q is the ratio of observed variance with within study variance, right? So I would say the observed variance is same, right? It looks that, let's just see. Yeah, it's same, right? You can see the observed variance is same for both the studies. It's same within study variance. So you can see within study variance is more for A, right? You can see these confidence intervals are much wider for A. So within study variance is more for A. So naturally you would expect that the value of Q will be less for A and it will be more for B, right? This makes sense. Now we'll compute Q minus degrees of freedom, which is the excess dispersion. So now you know degree of freedom will be same only because number of studies is same for both the studies, and because Q is higher for B, so Q minus DF will also be higher for B and it will be less for A. Makes sense? Now you can see Q minus DF, because it is more for B, so P value will be closer to 0 for B than for A. Also making sense? You can see P value is closer to 0 for B and closer to 1 for A. Now we have to compare the t-square statistic. So remember, t-square statistic depends on two things. First is the excess dispersion, and you can see already that excess dispersion is more for B. What is excess dispersion? It is Q minus DF, right? So Q minus DF is more for B. So you would expect that the t square will be more for B, and this is what we are seeing only, that t square is more for B. Because t square is more for B, obviously t will also be more for B. So what is the importance of this t now? That is what I want to tell you. So now you can the summary effect that was computed for this forest plot was actually 0.41. Let's imagine. So now you can compute a 95% confidence interval of true effect size by using this standard deviation and using this summary effect. So the formula will be simple. It is 0.41 plus minus 1.96. That will be the critical value of Z, right, for 95% confidence interval multiplied by T. So you know the T here is 0.193. Remember, this T is the standard deviation of the true effect. So when you are computing this 95% confidence interval, what you are getting is basically the 95% confidence of the true effect size. So this can give you an idea of what is the range within which 95% observations of the true effect size will lie, right? So this will come out to be 0.04 to 0.79, and this is been shown here like this bell shaped normal distribution curve. So you can, what you can see is that this is the variation in the true effect size for this forest plot. Similarly, for this forest plot, because the t value is more, the 95% confidence interval will be wider. Can you see this is much wider as compared to this, right? So for this study, the true effect size, they lie in a relatively narrow range, right? There is only a limited narrow range. The 95% CI is narrow for A, whereas for B it is wider. See, this is in contrast to the actual within study variance, right? Within study variance is actually much more for A. Can you see within study variances are much more for A than for B? But if you will look, the 95% CI that we have generated for the true effect size, that is actually much wider for B than for A. Okay, so for B, you can say there is a bigger range for how much true effect size can vary from study to study, but for A the range is relatively narrow. And of course this has practical implications. Imagine if the mean effect size, the summary effect is similar in both the studies, right? It is same only in both the studies, it is 0.41, but in this study the range of that true effect size is narrow, and in this study the range of the effect size is wider. So this intervention looks more reliable. Like imagine if 0.41 is a good effect size, it is a like a maybe some whatever effect size index this is, but let's say an intervention works by 0.41, right? But the variability that you can expect is let's say 0.3 to 0.5. versus in another intervention which also has an effect size of 0.41, but maybe it has a range of much wider, 0.2 to 0.6. So which intervention would look more reliable? Obviously first intervention would look more reliable. So that is the practical implication of this 95% CI of true effect size. It gives an idea of how much variability you can expect in the true effect size, right? So this gives you an idea of expected distribution of true effects. In A, it is relatively narrow, which means that it captures only a fraction of the observed dispersion, and the rest is assumed to reflect error. So what it also means is that most of the dispersion, see, only a part of the dispersion can be accounted. This much dispersion can be accounted by the true variation in the effect size, and the rest of the dispersion here, whatever rest you are seeing, that is due to random error, right? But here in B, another thing, something you can conclude is that the 95% CI is accounting for literally all the dispersion, right? Can you see that most of the dispersion is due to the true effect size only, right? So this is what is being shown by the I-square statistic also as a numerical value. Okay, let me repeat this concept. This is an important concept. See, you can say that this is the 95% CI of the variation in 95% CI of the true effect size, how much variability is occurring in the true effect size, right? So let's draw a line here, this line and this line. So whatever confidence intervals you are seeing within this range, this may be somewhat, you can say, theoretically this may be the true variation, but this you cannot account for true variation. What is this? This is probably some random error, right? So that is in A. But in B, if you will make a line here, this is the 95% CI, this is the 95% CI for the true effect size, then you will see that literally all the variation, most of the variation that you are seeing, right, that is accounted by nothing but the variation in the true effect size. So that is the concept of I-square statistic. So you can see that 89% of the variation is due to true effect size variation, and rest of the variation is due to random error. But in here the I-square statistic is less, means only 58% of the variation is due to you can say this much, 58% of the variation is due to the true variation in effect size, but the rest of the variation, 100 minus 58%, this could be due to random error. So this is the concept of I-square statistic also, that how much proportion of the variation is the true variation. Okay, so that is clear, I hope, right? Now we'll compare C and D. So we'll start from the concept of Q. Again, you know, Q is a ratio between observed variation and within study variation. So first we'll see observed variation is more for which forest plot. This is the method that I use, which I find relatively easy. So you can already see the observed variation looks much wider, right? Can you compare these two graphs? Sorry, not graphs, forest plots. You can say that I think observed variation looks much more for D. Okay, so I'm going to write here observed variation looks much more for D. Then we'll talk about within study variance. So within study variance is this much, right? How much wide these confidence intervals are. Again, it is much more for D. So basically what is happening is that both observed variation as well as the within study variation, they have been increased from C to D. As a result, the ratio will still remain same, because Q is the ratio of observed variance with within study variance. So Q statistic will remain same, and Q statistic is actually same for C and D, right? So it makes sense why Q statistic is coming same for C and D, because both the observed variation as well as the within study variance has been increased. This much is clear. Now we'll move to Q minus DF. Because Q is same and DF is also same, because number of studies is same for both of these forest plots. So Q minus DF will also be expected to be same. Then p-value, you know, p-value is basically testing this Q statistic only. P-values are based on Q statistic only. So they will also be same for both C and D. Now very important is the t-square. So remember, I told you t-square depends on two things. First is the excess dispersion. Where is the excess dispersion? This right here. This is showing you excess dispersion. But another important thing that it depends on is the absolute scale of the absolute dispersion. And you can see Okay, I'll ask you, where is the scale of the dispersion more? The absolute scale is more for D. So even though excess dispersion is same in C and D, right? Excess dispersion is same, but the scale of the dispersion, it is more for D. Because the scale of dispersion is more for D, T square will be more for D as compared to C. We have discussed this before. So T square will be more for D as compared to C. Why? Because even though excess dispersion is same, the scale is more for D. Then similarly T will be more for D because T square was more. Now you can compute the 95% confidence interval of the true effect size. So the like the summary effect is not given here, but whatever be the summary effect, let's say summary effect is M, then M plus minus 1.96 into T. So this will be a 95% confidence interval for true effect size. This they have computed and they have shown you in the form of this normal distribution curve. So basically what this means is how much of the variance is the variance due to variation in true effect size. So let's draw a line here. We'll draw a straight line to understand the concept. So you can see that this much variance, I'll draw this, delete this part. So this much variance, right? This much variance is due to the variance in true effect size, right? And what about this variance, this rest of this variance? You can say this variance, this, everything else that's remaining, that is random error, right? This is how you can understand this theoretically. And here in this forest plot, what you can see is the 95% confidence interval is much wider. Why? Because the value of T is more, so 95% CI will be wider, right? So this much is contributed by the it is the true variation in the effect size, right? Whereas the rest of it, this part, this is probably due to random error. So now the thing is that I square statistic is still same. Why? I square statistic is what proportion of the variance is contributed by the between study variance or the true variance in effect size. So in both of these cases you can see that here in case of C, this, let's say this much is the total variance, right? And 58% of that is contributed by the variance in the true effect size. In D also, if this is 100% variance, then about 58% is contributed by the variance in the true effect size. So I square is still same, right? Because I square is not it is not based on the scale. I square does not depend on the scale of the dispersion. I square is a rather proportion. So it will ask the question, what proportion of the total variance is contributed by the true variance in the effect size. So I square will remain same, right? It looks same also visually, if you'll see, right? If this is the 100% variance, then 58% is contributed by I square. Similarly here also, if this is 100% variance, 58% will be contributed by I square will be contributed by the the true variation in effect size, right? So Bell, even though the curve is wider for C than D, but the total dispersion is more also for C and D. So I square statistic will remain same and a comparable proportion of the effect fall in the range of the curve because the ratio is the same. Okay. So some final remarks. First, this I have already told you, the importance of T is it enables us to have a discussion on the importance of the dispersion. So this example I have already taken, but I'll repeat it. Suppose an intervention has a summary effect of 0.5 and the T comes to be 0.10. Then if you will compute the 95% CI, it will be 0.5 plus minus 1.96 into 0.1. Right? So the 95% CI will come out to be like this, 0.30 to 0.70. Clear? Let's imagine there is another intervention which also has a summary effect of 0.5, but this time the T is 0.20. So 95% CI will be much wider. It will be 0.1 to 0.9, right? So the problem, and if let's take third intervention, T is 0.30, then the effect size, the 95% CI will change from minus 0.1 to plus 0.1. So even though the summary effect is same for all the interventions, the summary effect is 0.50 only, the implication of this changes because of change in the 95% CI of the true effect size. right? So we need to attach value judgment to these ranges. What range is harmful, what range is trivial, what range is useful. Maybe somebody will say this range is useful, this range is trivial because there is too much variance occurring in the true effect size, so it is not reliable. Maybe somebody will say this may even be worthless because the variance is the true effect size, the effect size is going in negative also. So we need to have a practical discussion on the implication of this range, or the implication of the 95% CI of the true effect size, right? So this is the practical, the intuitive importance of the T statistic, right, or the standard deviation of the true effect size, right? And of course we'll discuss how to compute the 95% CI of this T also. So that's all for T statistic. In next discussion I'll talk about the last statistic, that is the I square statistic, and then we'll be having some discussion on computing the 95% CIs of these statistics.